All right, welcome to this next video. In this next video, we continue to sketch our functions. So here we're given another complicated function to the degree of 5. Let us see if we're able to sketch it using our derivatives. So just as a reminder, the first thing we're doing when sketching these graphs, we need to be able to find our intercept. And just a reminder, in the Cartesian plane, two-dimensional, we have two. So the first one is going to be the y-intercept, and the second one is going to be the x-intercept. Let's see if we're able to do that. We know for sure with the y-intercept, it's where x is 0, so we have that as 0. So the coordinate 0, 0 is what's going to be our intercept. And then here we have 0 equals to... We can factorize x to the 3 out. We're left with x to the 2 minus 5. And therefore, we have 3 x-intercepts. The first one is going to be x is 0. And then we have x equals to minus root 5. And then we also have x equals to root 5. So this will be our x-intercept. Cool. The next thing we then want to do is to focus on our turning points. And we also know that at our turning point is where the derivative is equals to 0. So let's see if we are able to do that. Okay, so what we want to do with our turning points is just make the derivative equals to 0, and then we'll take the derivative of that, which gives us 5x to the 4 minus 15x squared. So let's see if we can factorize these and see if we can solve it for ourselves. So this is x squared minus 3. So it does leave us with 3 turning points. X is 0, x equals to minus root 3, and x equals to root 3. So what I then recommend, let's find the corresponding y values for those. And the corresponding y values for those will be, if you plug 0, that's the answer that you get. If you plug in f of minus root 3, we end up with an answer of 10,4. Or an approximation of that, closest to that. And then if we happen to find the point root 3, we end up with a negative 10,4. Okay, this looks a little bit symmetrical so far. Let's see if we are able to do this. Okay, so the second thing we want to do, which I'll just save up some space for us to get done here on the side, is to start classifying these turning points. All right, so when classifying, we need the second derivative. Okay, but I'll do two things first. So what I want us to do is we will see if we can do that. So we'll get the derivative, the second derivative, which gives us 20 x to the 3 minus 30x. So that's what that is. And then from here, I'll start seeing if I can classify these turning points already. So let's classify the turning point. So what I then want to do with the turning points, as a matter of just classifying them, I'll just put them into the derivative. If we plug in 0, so the second derivative where we plug in 0, we can clearly see that gives us 0. The second derivative, and we're using minus root 3. If we do that, we get a solution of minus 30 root 3. And because this is negative, it means the turning point minus root 3 is going to be a local maximum. So this will be a local max because it's negative. And then if we want to find the second derivative when x is root 3, we see that gives us 30 root 3. Plug into your calculator, and you will see that this is positive. So therefore, that gives us a local minimum. So quite important for us to know. The second thing I want to do is to deal with the points of inflection as part of the stationary point, point of inflection. So basically, from our equation of the second derivative, we just equate that to 0 and see what x values we get. So if we do this and get 0, x to the 3 minus 30x, we get the following. We get that x is 0, or we get x equals to minus root 6 over 2, or we also get x is equals to root 6 over 2. So quite important. So we now need to get the respective y values. That will give you 0, minus root 6 and 2. Let's plug this into our calculator quickly. We get 6,4, and then this one over here, let's plug in this point root 6 over 2. We end up getting 6,4, negative 6,4. So this is the function that we then have to sketch using the information that we have. So let's see if we are able to then sketch a function of this type. Okay, so I'll keep going up just to refer back to the information that we've just used. So just as a reminder, some of our key points here is minus root 5, and positive root 5 will be our x-intercept. Just as a reminder, we also remember that our turning point will be at minus root 3 and at plus root 3. But we also know that at root 3, we've got a turning point there as well. So this is going to be approximately 10,4. So that's where minus root 3 is going to be. And then we also know that at this other point as well here, which is a turning point, we also know that this is a local max from what we've just identified. This will be a local minimum. This is also going to be minus 10.4, just an approximation of that. And this will be root 3, which is quite important for us to know. And then in between that, we also have minus root 6 over 2, which is a point of inflection. We also have root 6 over 2, which is a point of inflection. And we know that this root 6 corresponds to a value close to 10, which is approximately 6.4. You can work out that. And then this is another value somewhere there close to 10, which is a point negative 6,4. So I think because of this, and then we have 0, which is both a turning point, point of inflection, and so forth. From there, we are able to then sketch our graph. Because we know that we're heading towards a local maximum, it means that our gradient here is positive. So as we go down over here, our gradient is positive. All right, so that's how we would sketch this graph. And because this is a local minimum here, we know that going to our x-intercept there, our gradient will now be positive. So our function is starting to take some shape. We also know once we get here, we'll have a turning point, and then turning point changes the gradient. So this will be the point there. I want to make it with a slight curve there so that you see that the gradient was going down. But now this is a point of inflection once you get there. So this curves again, there changes concavity. Once you get there, this is a turning point and a point that changes concavity. So concavity will go down again. And then once concavity gets to this, concavity changes direction again. And then once you get there, you've got a turning point. Boom. And that is more or less the function that you're looking for. So it's important that you know the properties of these functions and how they behave. What I will do in the next video is start dealing with functions that are rational, that have got asymptote. And we'll start with the first video then. I hope this is starting to make some sense on how we sketch these graphs. And therefore, I will see you in the next video.